This video covers the second half of section 3.4, Proving Conditional Statements Using Direct Proofs. We're going to look at some proofs involving the divisibility relation from elementary number theory. First, recall the definition from section 3.2. An integer b is divisible by an integer a not equal to 0, or a divides b, which is denoted with a vertical line, provided that there exists an integer k such that b is equal to ka. For our first example, let's prove for all integers a, b, and c with a not equal to 0, if a divides b, then a divides bc. Our first step is to write it in symbolic form. So we have for all a not equal to 0, for all b, for all c, a divides b implies a divides bc. The domain for our variables a, b, and c is the set of integers z. So we start our proof with a proof by arbitrary element. We're going to suppose a, b, and c are arbitrary integers with a not equal to 0. We suppose the hypothesis a divides b. We then need to show the conclusion a divides bc. To show this, we go back to the definition of divides, and we need to show that there exists an integer k such that bc is equal to ka. We now have an existential statement, so we need to start an existential proof. So we'll set up our two columns. We need to find a k, and then we need to verify that our k satisfies our two conditions, the domain and the propositional function. In order to find our k, we're going to use our hypothesis that a divides b. Since a divides b, then there exists an integer l such that b is equal to la. If we multiply this equation by c, we obtain bc is la times c, which we can regroup terms and rewrite it as lc times a. Now, comparing this equation with our propositional function bc is equal to ka, we see that this has the form of our propositional function with k replaced by lc. So this tells us we should choose our k to be lc. We're now ready to go over to the right-hand column and check our domain. Since L and C are integers and Z is closed under multiplication, then we can say that K equal LC is an integer. And then from the work on our left, we can see that our propositional function holds. Okay, this proves the existential statement, and so therefore our conclusion, A divides BC, must be true. For a second example, we'll prove something a little bit more complicated. We want to prove for all integers a, b, and c with a and b not equal to 0, if a divides b and b divides c, then a divides c. So our first step, as usual, is to write it out in symbolic form. So we have for all a not equal to 0, for all b not equal to 0, for all c, a divides b and b divides c implies a divides c. And the domain for our variables a, b, and c is again the set of integers z. So this is a universal statement with three universal quantifiers. So we're going to start our proof by using a proof by arbitrary element. So we suppose a, b, and c are arbitrary integers with a and b not equal to 0. We suppose the hypothesis a divides b and b divides c. We then need to show the conclusion a divides c. To show this conclusion, we go back to the definition of divides, and to show this, we need to show there exists an integer k such that c is equal to ka, or in symbolic form, there exists a k in z such that c is ka. We now have an existential statement, so we need to start an existential proof. We set up our two columns. We need to find a k and then verify that our k satisfies our two conditions. To find our k, we're going to use our hypotheses. So, since a divides b, there exists an integer l such that b is la. Since b divides c, then there exists an integer m such that c is mb. And we can combine these two equations, substitute b is equal to la into c is mb, and we obtain c is mb, which is equal to m times the quantity la, which is equal to ml times a. And if we compare this to our propositional function, we can see that this has the form of our propositional function where k is equal to ml. So that tells us we should choose our k to be ml. So we've now found our k. We're ready to go over to the right-hand column. And since L and M are integers, we can use our usual condition that z is closed under multiplication to conclude that k equal ml is an integer. And from the work on the left, we've got c is equal to the quantity ml times a, and ml is k, so we get c is equal to ka. So our propositional function holds. So this proves the existential statement, which then proves our result, and so thus our A divides C. For another example, let's disprove a statement. We want to disprove the statement for all integers a, b, and c with a not equal to 0 if a divides bc, then a divides b, or a divides c. First, write this in symbolic form. So this is a universal statement, and now to disprove a universal statement, we need to either find a counterexample or equivalently show that the negation is true. The negation of the statement is shown. There exists an a not equal to 0, there exists a b, there exists a c, such that the hypothesis a divides bc is true, and the conclusion is false, which, applying De Morgan's law, means that a does not divide b and a does not divide c. So we need to show that there exist integers a, b, and c with a not equal to 0, such that a divides bc, but a does not divide b and a does not divide c. So just by guessing, okay, we can choose some random numbers or just choose some numbers using educated guessing, and I'll choose a is equal to 6, b is equal to 4, and c is equal to 3. And we can compare, well, check that these satisfy our conditions. Obviously a, b, and c are all integers, and a is not equal to 0. And bc is equal to 12, so 6 divides 12, so therefore a divides bc. However, a does not divide b, so 6 does not divide 4, since there does not exist an integer k such that 4 is equal to k6. And a does not divide c, 6 does not divide 3, since there does not exist an integer l such that 3 is equal to l times 6. So we've found a counterexample, or we've found integers which satisfy the negation of our statement, so this tells us that our statement is false, and this disproves the statement. The next thing we want to consider is proving biconditional statements. So to prove a biconditional statement of the form for all x, p of x if and only if q of x, we can use the equivalence. Okay, the biconditional is equivalent to two separate conditionals, and so this is equivalent to for all x, p of x implies q of x, and q of x implies p of x. And we can actually distribute the universal quantifier over the two conditionals, and so we obtain two separate universal statements with conditional propositional functions. And so this shows to prove a biconditional statement, we can equivalently prove two separate conditional statements. For all x, p of x implies q of x, and for all x, q of x implies p of x. The first of these is referred to as the forward direction, and the second as the backward direction of the biconditional statement. This method is called the proof by separate implications of the biconditional statement. Now we can use either a direct proof or any of the other methods of proof that we're going to develop later in the course to prove each of these two conditional statements. And very often we may need to use different methods for the two statements. For example, let's suppose we want to prove the sum of any two integers is even if and only if the difference of the two integers is even. First step, rewrite this in standard form. This is equivalent to the statement for all integers m and n, m plus n is even if and only if m minus n is even. And this has symbolic form. For all m and z, for all n and z, m plus n is even if and only if m minus n is even. To prove this biconditional statement, we then need to prove the two separate conditional statements. For all m and z, for all n and z, m plus n is even implies m minus n is even, and for all m and n and z, m minus n is even implies m plus n is even. So I'm not going to prove these in the notes here, and this is actually going to be similar to one of the homework problems. And so the point is, to prove the biconditional statement, you'll need to prove these two separate conditional statements. You'll notice that there's a couple typos in the notes here. There's a couple extra parentheses around. You can just ignore those. Now for some biconditional statements, p if and only if q, we may be able to construct a chain of biconditional statements of the form p if and only if q1, q1 if and only if q2, q2 if and only if q3, and so on, all the way down to q sub n if and only if q. And we can prove the biconditional statement p if and only if q directly without proving these two separate conditional statements, and this method is called a direct proof of the biconditional statement. We'll see an example of a direct proof in the next section. We have one last topic in this section that I'm going to touch on briefly here, and that is vacuous and trivial proofs. These are two methods of proof for conditional statements that occur in very special situations. In a vacuous proof of a conditional statement for all x, p of x implies q of x, we show that the hypothesis p of x is false for all elements x in the domain. It then follows that the conditional propositional function p of x implies q of x must be true for all elements x, which implies that the universal statement is true. In a trivial proof of for all x, p of x implies q of x, we show that the conclusion q of x is true for all elements x in the domain. It again follows that the conditional p of x implies q of x is true for all elements x, which tells us again that the universal statement must be true. We'll see some examples of vacuous and trivial proofs in some of the later sections.